I'm Samantika Sury. Thank you very much for inviting me out here. I'm very excited to be here. I'm going to be talking about a new technology, a series of technologies we're developing at Samsung called memory-coupled compute. And we truly believe this can be game-changing technologies for the future of HPC and AI. As Vitali mentioned, I'm in Samsung in the Samsung Advanced Institute of Technology as part of Systems Architecture Lab. This is a new lab that we've set up. I'll talk a little bit about it. I have a lot of material. I'll get through it, but it's mostly a sampling of all the technologies we have to address HPC and AI. I'd be very happy to discuss with you all in more detail. If you all have questions through the day I'm around, please find me, and I'd be more than happy to talk to you about it. This talk is made in collaboration with several partners from our Samsung Institute of Technology and various labs, and they're listed here. Our Systems Architecture Lab is a newly formed lab. It is really new. It was formed in this year. And the goal of this lab is to develop the most innovative technologies for HPC and AI. We're really focusing on data communication out here. And so our strategies are really to look at breaking through the memory and communication walls. As we just saw in our previous talk, there's been a lot of improvements in compute efficiency. That's why we got to the exascale era. It's our contention that the post-exascale era is really going to be dominated by data movement, and that's where we're really going to be focusing our attention. And so you'll see through our technologies that we're really providing some very significant advancements in memory and network bytes per flop. And we're doing these through these two technologies that we're calling memory-coupled compute. This isn't processing in memory. This isn't processing near memory. I'll talk about how this differentiates from there. This is a new paradigm called memory-coupled compute. And we are pairing this memory-coupled compute technology with what we're calling supernodes. And I'll give you a slight flavor of what we mean by that as well. And as was evident from the previous talk as well about OLCF and how Frontier got where we are, we're really driving innovation in system-level energy efficiency and cost, because it turns out that you can provide the most flops, you can provide the most bytes, but what really limits you is cost, as we saw, and so we're really driving that from day one. Okay, so before I start, how did we get to memory-coupled compute? So if you look at the chart that you've seen on the right out here, and you've probably seen this several times, we've all looked at it. This is the top 500 list, right, over the several years. And, the three charts are very nominal, right? The sum of all the machines, the top machine, and the 500th machine. And what I've plotted on that is Moore's law, or rather effective Moore's law, right? 2x every 2 years. And you find that the supercomputing chart is 2x every 1.5 years. Turns out we've been beating Moore's law in the supercomputers we've been building. Who would have thought that, right? And we're not really doing that because we're taking transistors and putting them together, right? How would you beat transistor technology by doing that? No, we're doing that because we're making architectural shifts, paradigm shifts in how we are putting these transistors together. So if you look at how we've been getting that 2x every 1.5 years, we started with vectors, right? Cray, they gave us the first big boost. Then we moved into more clusters, right? Multi-programming, that's sort of the Beowulf clusters. Then we basically said, okay, how can we take that and scale out the transistors? So that came the multi-core era, the multi-thread era, and we lived in that era for a really long time. In fact, we still are. Many of the top 500 machines are really very focused on the multi-core era. Then came along Blue Gene that you all are very familiar with, and what did that give us? Massive amounts of parallelism. Blue Gene said, let's go simple, let's go scalable, and let's make the whole thing very parallel. That gave us the next shift to stay on that curve that you see out there. But then that era came to an end, right? Dennard scaling, as coupled with sort of the slow in Moore's law, meant you couldn't just scale up as is. Data movement also started playing a big role. And so we were limited by memory bandwidth, we were limited by communication bandwidth. Blue Gene really built a very scalable network. We found we couldn't push that anymore, so we had to make a dramatic shift in the compute side. And that's where heterogeneity came in. We moved towards GPUs, we moved towards different types of accelerators, and we're staying in that era, right? And looks like that era is getting us very good performance, it's getting us very good energy efficiency, and it's getting us very good overall scalability. And so we're in the heterogeneity era. So now what's the next discontinuity, right? How are we going to continue to stay on that 2x every 1.5 years that we'd like to stay on for the supercomputing chart? And what we're really talking about out here is, what I mentioned, that we basically had efficiencies in compute, efficiencies in communication, efficiencies in memory working independently, and paradigm shifts in that. For memory coupled compute, we're bringing them all together. We're tightly coupling both compute with memory and communication. And this is going to be the next discontinuity that keeps us on that top 500 chart that we want to be. So, I'm going to talk a little bit about the motivation, why we settled on MCC, or memory coupled compute, as our vision for the future. And then I'll explain a little bit more about the technologies that are going to get us there. So as you can see that, don't just take my word for it. The memory and communication wall is certainly getting higher and higher. On the left, I have a plot here just of technologies that are advancing flops across all the processors and some of the accelerators that you see, as well as the technologies to drive memory, starting with DDR, GDDR, HBM, all the way up to HBM2 and even HBM3 that's going to be coming, and then the network technologies. This isn't exhaustive. This is supposed to be a flavoring. So there's PCIe, there's some NVLink. But what's the key thing you can see from this plot on the left? Our flops are increasing at a dramatic rate. That's why we could get to our exascale machines. Our memory bandwidth, our network bandwidth, not so much. In fact, it's really struggling to keep up. If you looked at a plot with flops, memory bytes per flop and network bytes per flop, it's quite an inversion. We've been going down on the memory bytes per flop and the network bytes per flop, and just going up on the flops. This is not scalable for real application performance. It's great for LinPack, it's great for getting some of the exascale numbers, but real applications need data to process on. Real applications need to communicate, they need to exchange data between ranks, between PEs, whatever be your programming model. At some point, this dichotomy where we are increasing flops but not increasing the way to get those flops into the system is going to come crashing into each other. This isn't just for HPC, right? AI training models are getting larger and larger. The chart on the right shows you how transformer sizes are increasing, but the memory to store them, both in capacity as well as in bandwidth, isn't growing at the same rapid rate. So how can we keep building larger and larger AI models if we can't feed them, if we can't store them? So, what we found is that across, when you sample all applications, right, modern sim applications are really memory bandwidth limited. And AI applications, by and large, are what we call communication limited. A lot of HPC, traditional HPC applications also get communication limited, but they tend to work better with weak scaling, and they're able to live with that. But the AI applications really get communication limited. So the other thing I want to point out is that the previous chart was just about technologies, right? It was just showing you hard numbers. This actually translates into actual application performance itself. This divergence that we have between compute flops and memory performance really impacts applications. If you see this plot on the right, this is from a paper not too long ago. It wasn't done with the most current machines. They were more Xeon machines in the 2018 era. But what it basically shows is that even HPL, which you would expect to be an extremely compute-limited application, tends to utilize about 25% of its execution time just bringing in data. That's just HPL, right? That's the one end of the extreme. The other end of the extreme, which is closer to streams or some memory bandwidth limited applications, you can use about almost nearly 100% of all the available memory bandwidth. Not just that, these applications tend to be very bursty in the way they access memory. So there tends to be high amounts of bursts of getting data in, operating it on some time, and then again high amounts of burst of data. So this can't just be I need a lot of slow and steady data movement. I need to provision for sustained data movement and sustained bandwidth into the system. I also need to be able to provision for these phases of extreme amounts of memory bandwidth while maintaining the energy efficiency that we want to maintain for our systems. So there are a lot of challenges here. This isn't an easy problem to solve. If we could just take one thing, which is computes, and say, I just want to make that more energy efficient, we might have a solution. If you want to just take memory and say, oh, I want to make that more efficient and forget about the compute, I can do that. If I just want to take communication and say, I want to make that more efficient, we'll reach a third point. But if you want to make all three together, these three vectors don't really intersect very well for us to be able to come up with a very easy solution. This is why we're trying to solve this particular hard problem. As it turns out, that increasing the memory performance tends to help both the memory and the communication performance. They're sort of tied together more than the compute and memory by themselves. And so when you couple those two together and then you add the compute along with them, you can actually improve the application performance significantly. So we took a couple of real applications. There's stochastic gradient based on a lot of ML applications are based on that. And we took Lulesh, a classical application from many of the procurements that we've used so far. And we looked at what's really limiting their performance. So we basically just scaled them up, very simple, didn't do anything major with the actual kind of programming models. And you find that while in some of the stochastic gradient applications, you would expect about 50 to 60% of their execution time was spent in compute, and we see that reflected here. About 40% of its execution time is being spent in actually bringing the data to that compute. So that's significant out there. But look at something like even a classical Lulesh-like application. There are phases that are very memory bandwidth bound. There are phases that are spending a lot of time getting data into caches, getting data from memory. So what I'm trying to show out here is that, yes, this is a memory bandwidth problem. This is also a memory latency problem. So, there's a saying, great bandwidth and bad latency never gets you good performance. So, now I threw in a fourth vector out here. I said memory bandwidth, I said communication bandwidth, I said compute, and now I'm saying we need all these three at decent memory latency. We at least can't go inverse on the memory latency curve. Otherwise, we won't be able to fix applications like Lulesh. So what we looked at is, we now need to understand how we can couple all these four challenges and vectors together. And the final thing is energy efficiency. As Tom just showed us, energy efficiency isn't getting better by itself. We need to fundamentally do something to bake that in this. You all must have seen this chart. This came at the early start of the path forward time frame and the ECP time frame, where John Sharp just looked at the general trends of how energy was being expended amongst flops, amongst on-chip communication, all the way up to off-chip communication. And what we found then, and what has stayed pretty much true, is that while compute efficiency tends to go up better with transistor scaling as we get to newer and newer technologies, communication efficiency is not. The resistance in wires, in cables, etc., is fundamentally hurting us. We're not able to get as much efficiency in communication. So I'll circle back to what I said in the beginning of the talk. While the exascale era was really dominated by compute performance and making sure we can get that, the post-exascale era, the machines that are going to come after the Frontiers, the LCAPs, and the Aurora machines, are really going to be dominated by data movement. Okay, so now that I set the stage for why we are really trying to attack the memory and communication wall, let me talk a little bit about the technologies we have in store for you that we believe can address that. So the first one, of course, is the classical HBM technology. This is the 2.5D. This is the backbone in terms of the GPU memories, as well as some of the CPU memories for the exascale machines. HBM fundamentally changed the landscape for memory, right? It's my contention, without HBM, GPUs would not have performed as well as they did. If you paired DDR with GPUs, they would not have been able to achieve the peak flops that was on paper for them. So HBM really came and gave that a big boost. So that's the era we're in now. The next era, which Samsung's really pioneering, that stayed in research for a very long time, but that we are productizing now, is what we're calling PIM, or processing in memory. And I'll talk to you a little bit about the PIM technology we have, how we plan to deploy it, and what it means for you for AI and HPC. And what PIM really is embedding actual flops into the memory cells. So that's the closest you can get in terms of data movement, right? You're basically taking memory cells and putting actual execution units in there. There are limitations, as you can imagine. There's only certain types of computes you can do. There's only certain amounts of computes you can do. There's certain kind of software models you have to maintain. But that can really be a game changer for applications that want to do very simple, very structured kind of computes. And many AI applications actually do that. And then the third sort of way we want to attack the memory wall is to take this up to the next dimension. We really want to make true 3D stacking possible. And this is what memory coupled compute is. It's really stacking memory with compute. I won't go into a lot of details about how this technology works, right? Because all of that is very proprietary information. But this truly is the next level of integration of compute with memory. So if we make this memory coupled compute vision a reality, what will this give us? This will reduce power consumption more than 2.5D, right? It will reduce latency more than 2.5D. It will also give us a more generic programming model than the PIM programming model, and I'll explain why that is. So in a sense, memory coupled compute gives us the best of both the worlds that we're used to. We like the 2.5D world because of the general purpose compute we have with it. We like the PIM world because of the advantage you'll get with latency and power. And so we want to make memory coupled compute sort of the best of both. And there have been research, there's been a lot of work about how you can do it, what might be some of the things you may do it, but nobody's really looking at this from a real world technology perspective. What are the constraints to make it happen? And Samsung is in the best position to do that, right? We're the world leading memory and silicon technology provider, and so that's why this is the hard problem we are taking on now. Okay, so to motivate what memory coupled compute will really do for you, let me spend a couple of slides talking about 2.5D and PIM. I'll be really quick on this because there's a lot of material out there for you to read more and learn more, but I just wanted to give you a flavor. So when you go ahead and read that, you'll have some context to go along with it. So our 2.5D, right, which we're sort of used to, these are through interposers and MDFI connections between memory and compute, give us this high bandwidth that we like. Gives us latency, which is at par with DDR latency, a little bit higher based on some of the memory controllers optimizations that have to happen, but mostly on power. And most importantly, we can build very flexible SoCs, CPUs, GPUs, accelerators, right? They all tend to use HBM as they need. However, we find that the substrate can be very expensive. Not just that, the pin limitations to actually connect them, those limit how much bandwidth we can drive. So even if Samsung can go ahead and build technologies with much more memory bandwidth, the physical connections, 2.5D on the substrate to connect the memories to the CPUs are limited. They're limited by the CPU balls, they're limited by the PCB wires, and they tend to be the fundamental limiter in how much you can scale that bandwidth. The off-die signals also take latency, they take power, and they take area. And so then you have to make a trade-off. If I build a very large SoC, maybe I can't build enough HBM to go along with it. And that forces us into how much compute versus how much memory. We want to free you from this challenge of having to make those trade-offs. So that brings us to PIM, right? What does PIM do? PIM basically says, look, even HBM bandwidth, right, as it is, isn't enough for some specific workloads, right? They can benefit from even more bandwidth. Not just that, they have certain loops which have very simple computation in them. Matrix multiplication, simple matrix vector multiplications, simple jumps, simple reductions. And they need almost 4 to 5x bandwidth more than what you can get just from HBM. So then comes along PIM. What PIM did, and Samsung was one of the first companies, and others have followed suit, but Samsung is one of the first companies that built a prototype, right, worked with Xilinx, then worked with SAP, and is working with many other companies to build prototypes, study them, as well as then productize them. And what Samsung did was built this DRAM optimized AI engine inside a memory bank. I can't stress enough how novel this is. It's very hard to build efficient efficient compute in memory technology. Memory technology is not optimized for logic. Logic technology is not optimized for memory. Putting these two together in the same technology was, quite frankly, almost a fundamental shift that happened, and Samsung led the way to do that. So HBM, PIM, that's what we're calling Samsung's PIM technology. You may have heard FIM DRAM or something, but now the terminology for that is HBM PIM. Gives you more than a teraflop of embedded power with an HBM stack. If you think about that, one HBM stack, right, can get you about more than 600 gigabytes per second, depending on HBM2, HBM3 gets you more. In that contained HBM stack, you can get more than a teraflop of embedded computing power. It's really focused on FP16 and bfloat 16 at this point. You know, there is talk about expanding some of the operations, expanding the precision, etc. But the real target for that right now is FP16. And the way to think about it from a software model, and I'll explain more in the next slide, it's really a 16-wide SIMD engine. If you just had a SIMD engine, right, and you could basically just use your existing frameworks like PyTorch, TensorFlow, etc. And Samsung has put together software libraries that can directly intersect into those frameworks. So you can even run this with unmodified source code. That's the power of PIM. You can really use your, if you make modifications to use the specific PIM instructions, you get even better performance, but you don't have to. You can just layer it on top of the existing frameworks. Now there are some constraints, and I mentioned this earlier. The constraints really are that we have to be very compliant with JEDEC standards. If you all don't know what that means, this is a consortium that looks at latencies and wires, etc. for all memory technologies, and all companies come together for it. So Samsung cannot decide that HBM PIM, if it wants to be JEDEC compliant, doesn't have to meet the latency requirements and the signal requirements for reads and writes. We have to meet that. So that places a constraint on the kind of operations we do. They have to be very synchronous in that lockstep, right? You have to do one at a time, because otherwise, again, you can't meet the JEDEC standard. We can't at this point send off a loop to something like the HBM PIM and say, just go ahead and do it. If we could, that would really open the aperture for all that we can do in HBM PIM. But nevertheless, we can basically make reads and writes converted into simple adds, multiplies, MAC operations, etc. So, there are about 9 various kinds of operations that you can do, and in the next slide I talk about what they are. They're very RISC-V-like operations, but they can get you a good way forward in at least AI applications. The other challenge with something like PIM is that the way we made this happen is we took existing memory cells or memory banks and replaced half the cells, the data cells, with these PCUs or programmable compute units, right? So what does this do for you? Effectively, we cut our capacity, our HBM capacity, around in half, because we needed space to fit these PCUs. That's what you see out here. You have an HBM stack, and in order to fit these sort of PCUs, we had to eat up half the capacity. In future generations of PIM, we're bringing that overhead down. We're developing newer and newer technologies that allows that overhead to go lower. But it is still going to eat into your HBM capacity. And remember, we wanted the trifecta, right? We want compute, we want memory, we want communication all together. So we can't really get that if we do just PIM by itself. So before I move into memory coupled compute, I wanted to spend a couple of minutes more on PIM to just walk you through how PIM works. Right? So on the left, what you see out here, top left, is a classical HBM stack, and that's the HBM die. HBM modules, DRAM modules, are broken up into ranks and then into banks, right? And as you can see out here, they're clubbed into bank groups. So the way you actually access memory, right, you'll give a memory address. Bits of those physical address will select first your rank, then your bank group, the row, and the column, and that will take you exactly to the specific cell you want to read. So based on the physical address, you will pick out exactly one data element. This is how classical DRAMs work. PIM wanted to make something, at least Samsung's PIM wanted to make something where you could take the same stack and either use it for regular memory accesses or PIM-like accesses. So we keep the same process that I just described, except when you give a physical address, right, Samsung's PIM controller takes that and disregards the bank group and the specific bank address. And it says, okay, row and column across all banks can be accessed together. Okay? And so what that fundamentally does is now you can access the entire stack with a specific type of operation. And that's again a significant technology advancement without which we wouldn't have been able to take the same HBM stack and use it either for regular memory accesses or PIM accesses. So that's what we're showing out here, which is it basically ignores the sort of bank group and bank address and issues the instruction to all the banks. I already showed you here, which is each bank has this PIM unit. This is the logical way to think about it. Physically, we share a PIM unit between two banks because, we found that was efficient. And remember, we're always eating into our memory area the more the PIM units we put in there. There are 3 modes in which you can use PIM. I'll be really quick about this. The 3 modes that you can use PIM is single mode, bank mode, very similar to how you use HBM, all bank mode that I just described where you can send an operation to all the banks, and all bank PIM mode, where you can send the operation to all the banks and you can specify certain specific operations that are outlined in this paper that I put out here, this ISCA paper about exactly what operations you can do. As I mentioned, there's support for TensorFlow and PyTorch right now with PIM, and Samsung isn't stopping at just HBM. May not be very relevant for this audience, but we now have plans to extend PIM into regular DDR, we're calling it AXDIMMs, as well as into LPDDR. Okay, so there are LP PIMs. So we really want to change fundamentally all memory technologies with processing in memory. So all that's fine, right? But remember, I started this by saying PIM was great, but PIM had certain limitations in the instructions you could do, in the area that it was eating up, as well as in needing to maintain compliant with JEDEC. So you couldn't do like full offload of a loop, right? So what we're doing now next is we are doing memory coupled compute. And with that, we're basically doing true 3D stacking, and we're actually doing very fine-grained power sharing between the memory and the compute, so that our total memory stack ends up being this really efficient building block where you can put general purpose compute. We're exploring efficient cores, we're exploring AI accelerators, and I'd love to talk with some of the AI accelerator presenters after, in the lunch to see if there's some value add there. And we're trying to see how we can couple that with our memory. Now it turns out that we have 2 fundamental constraints out here that we're working through. One is the thermal constraint. Stacking memory on top of compute is a very, very hard problem. In order to maintain that memory working correctly, we cannot cross between 85 to 90 degrees centigrade. 95 is the outer limit. So we have a fundamental challenge as to how much compute we can put in there. And there's a lot of work that's gone into it where, they've said maybe between 60 watts of compute can drive and stay under that temperature. But Samsung's really trying to pioneer so we can even push that envelope higher. What we can get with this is very configurable bytes per flop, right? It isn't something like PIM where you're just dedicated with X number of programmable computing units with memory. We want this to be configurable so you can put different amounts of compute and different amounts of memory together. And then the other advantage with this is PIM complements this. Remember, PIM is in the HBM stack. What we're talking about doing is coupling that HBM stack with PIM with our compute. So you now get 2 types of compute, general purpose compute and PIM compute along with your HBM stack. So, the possibilities are quite high with this new technology. Okay, so I spoke to you about the memory wall, but I also spoke to you about a communication wall, right? It isn't enough for us to make tighter coupling of compute with memory. We now want to use this packaging efficiency that our memory coupled compute technology gives us to address the communication wall. To that, what we're trying to do is we're trying to build these supernodes, right? We're trying to take memory coupled compute building blocks and build supernodes with very high bandwidth and low latency fabrics between them. I can't go into a lot of detail about what these fabrics look like, but what they can give you really is some of the largest scalable domains in which to run AI applications. Think about it. AI applications or ranks that want to exchange data now can do it at a very high bandwidth and very low latency, much more than what we can expect from some of the exascale systems. Not just that, the way we are looking to build our supernodes, you get both point-to-point bandwidth as well as all-to-all bandwidth. So really, the application phases, it's great for collectives, it's great for reductions, it's also great for things like halo exchanges. So that's how we want to address the communication wall as well. And when we tested our technologies for a few types of applications with a few machines, I can't go into a lot of detail what these machines were. There are two plots that I want to show you. They're a little different, so let me explain it. The one on the left shows you performance, so higher is better. The one on the right shows you time to convergence or time to result, so lower is better. And it turns out when you put memory coupled compute, for a while until you get to a certain amount of flops, right, it tends to be competitive with some of the machines out there. But once you actually need a lot more memory bandwidth for a lot more flops, the memory coupled compute technologies tends to be very scalable. This is for a classical HPC application. And on the right, what you have is a classical AI application. So this is like a training model. And for this, as it turns out, the communication is the real dominating factor. So, until you get to a certain amount of computing power, you do strong scaling and it's able to manage well. But once you get beyond a certain amount, about 100 petaflops of computing power, then the memory coupled compute technologies, just vanilla memory coupled compute technologies, tends to do much better. If you couple our MCC with an AI accelerator as the logic element, we tend to do better all the way from the start. So this is only a flavor of a couple of early results we're getting with our MCC technologies. We hope to study this in more detail so that we can understand exactly what are the computes to pair together. Okay, now the last thing, and before I finish, is that I talked to you about memory latency, bandwidth, communication, capacity, right? What's Samsung doing about capacity? We've just announced in the news we're building these memory expanders based on CXL. If you are not familiar with CXL, it is a protocol that allows you to do both accelerator-to-accelerator communication as well as compute-to-memory communication. And using this CXL technology, Samsung's able to build a lot more data capacity in the same amount of memory. So, hopefully memory coupled compute, you all now know what it does and how it's going to get you cost, energy efficiency, and performance. I mentioned Samsung's very well positioned to do this. So, come innovate with us, share your thoughts and ideas with us as we take this new technologies forward. Thank you.
Any questions?
Yes.
Can you please differentiate between the memory-centric computing and the memory coupled compute?
This is funny. When we started thinking of the term to use, there is so many types of computings, right? Memory-centric, memory-based, in-memory, etc. I won't speak to what other people think about memory-centric computing, but memory-centric computing oftentimes means you have disaggregated memory pools, right? And you're doing some kind of compute in them, if you will. And this is quite different from that, right? We're actually saying we are integrating, we're not disaggregating the pools, we're sort of integrating memory with compute. So we're really coupling the two. But in a sense, I would say at a logical level, this is all talking about bringing memory closer to compute, if that helps. Yes? Can I take one more question? Okay, yes.
So you mentioned that this is tuned for BOS 1 and BOS 2. Mm-hmm. Do you have anything to say about BOS 3?
No, these two we know tend to be very memory bandwidth limited. So by and large, this helps other BLAST codes as well. But like AXP and GEM, when we studied, we got more than 4x performance improvement. So those are really the poster childs for it. I do have data for some of the others. If you want, I can pull up and show you later on. It's there in the paper. Okay, thank you.